Hello, my name is Kevin Benton, and I am presenting a research project that dealt with the mathematics from ancient Egypt. For almost 30 centuries, from its unification around 3100 BC to its conquest by Alexander the Great in 332 BC, ancient Egypt was the preeminent civilization in the Mediterranean world. From the Great Pyramids of the Old Kingdom through the military conquest of the New Kingdom, Egypt's majesty has long entranced archaeologists and historians and created a vibrant field of study all on its own: Egyptology. The main sources of information about ancient Egypt are the many monuments, objects, and artifacts that have been recovered from archaeological sites, covered with the hieroglyphs that have only been recently deciphered. The picture that emerges of its cultures with few equals in the beauty of its arts, the accomplishments of its architecture, or the richness in its religious traditions, or the advances in mathematics. King Menes founded the capital of ancient Egypt at White Walls, later known as Memphis, in the north near the apex of the Nile River Delta. The capital would grow into a great metropolis that dominated Egyptian society during the Old Kingdom period. The Archaic period saw the development of foundations of Egyptian society, including the all-important ideology of kingship. To the ancient Egyptians, the king was a godlike being, closely identified with the all-powerful god Horus. The earliest known hieroglyphs being written during this period. In the Archaic period, as well in other periods for most of ancient Egyptians were farmers living in small villages in agriculture, which were largely made of wheat and barley, formed the economic base of the Egyptian state. The annual flooding of the Great Nile River provided the necessary irrigation and fertilization each year. Farmers sowed the wheat after flooding receded and harvested before the season of high temperatures and droughts returned. The Old Kingdom began with the third dynasty of pharaohs. Around 2630 BC, the third dynasty king Deshur asked Imhotep, an architect, priest, and healer, to design a funeral monument for him. The result was the world's first major stone building, the Step Pyramid at Saqqara, near Memphis. Pyramid building reached its zenith with the construction of the Great Pyramid at Giza, on the outskirts of Cairo, built for Khufu, or Cheops in Greek, who ruled from 2589 to 2566 in BC. The pyramid was later named by classical historians as one of the ancient world's seven wonders. Two other pyramids were built at Giza for Khufu's successor, Khafra and Menkaure. The evidence of the use of mathematics in the Old Kingdom is scarce, but it can be deduced from inscriptions on the wall near a mastaba in Madian, which gives guidelines for the slope of the mastaba. The lines in the diagram are spaced at a distance of 1 cubit and show the use of that unit of measurement. So why did this first develop? Complex societies like Egypt required math to create buildings, manage food supplies, and compute the water levels of the Nile. The ancient Egyptians were renowned by the Greeks as masters of geometry. However, Very little evidence of complex Egyptian mathematics survives. Mathematics is also The mathematics was also developed in Mesopotamia, including the system of dividing time into units of 60 that is still used today for minutes and seconds. Higher math, such as deductive reasoning and logic, developed in Greece from 500 BC and onwards. The earliest true mathematical documents to the 12th dynasty are the Moscow mathematical papyrus, the Egyptian mathematical leather roll, Lunun mathematical papyri, which are part of a much larger collection of the Qanun papyri, and the Berlin papyrus 6619 all date to this period. The Renin mathematical papyrus, which dates to the Second Intermediate period, is said to be based on older mathematical texts from the 12th dynasty. The Egyptians also had many other mathematical accomplishments as well. An example of this is their calendar. It is from as early as 4800 BC, but in 4200 BC, their advances in mathematics and astronomy produced a 365-day calendar, 12 months of 30 days plus 5 feast days. By 3100 BC, various agricultural communities along the banks of the Nile were united by Nubian Menes, who founded a dynasty of 32 pharaohs and lasted 3,000 years. For more than half that time, Egypt included parts of modern Israel and Syria, as well as the Nile Valley. To rule effectively, an efficient and extensive administration was developed for taking taxes, census, and maintaining a large army. Another example of Egyptian mathematics was the Egyptian mace head. The Egyptian mace head contained a record of winnings of war of the pharaoh Namar, which contained 120,000 prisoners, 400,000 oxen, and 1.4 million goats. It is used a number system allowing counting to continue indefinitely by introducing, if necessary, a new symbol. All of this required some mathematics. At first they used counting glyphs, but even in 2000 BC, the higher tech glyphs were in use. The man behind this was Pharaoh Ramses II. Herodotus wrote about this saying, he divided the land into lots and gave a square piece of equal side, and produced of which he exacted a annual tax. If any man's holding was damaged by the encroachment of the river, the pharaoh would send inspectors and surveyors to measure the extent of the loss, in the order that he pay in the future a fair portion of the tax at which his property had been assessed. This maybe was the way in which geometry was invented and passed afterwards to the Greeks. The Egyptians had invented their own number system called the hieroglyphic numbers. The Egyptians had a decimal system using 7 different symbols. 1 is shown in a single stroke, 10 is shown by drawing of a hobble for cattle, 100 is represented by a coil of rope, 1,000 is drawing of a lotus plant, 10,000 is represented by a finger, 100,000 is represented by a tadpole or a frog, and 1,000,000 is a figure of God with raised arms above his head. The conventions for reading and writing numbers is quite simple. The higher number is always written in the front of the lower number, and where there is more than one row of numbers, the reader should start at the top. The Egyptians had also came up with a fraction system. All ancient Egyptian fractions, with the exception of 2/3, are a unit fraction. That is a fraction with the numerator of 1. For example, 1/2, 1/7, 1/34. In ancient stories, the god Seth attacked his brother, the god Horus, and gouged out his eye, then torn it to pieces. Fortunately for Horus, the god Thoth was able to put the pieces back together and heal his eye. In honor of this story, the ancient Egyptians also used the pieces of Horus' eye to describe fractions. The right side of his eye equals 1/2, the pupil equals 1/4, the eyebrow equals 1/8, the left side of the eye equals 1/16, the curved tail equals 1/32, and the teardrop equals 1/64. The Rhind mathematical papyrus is the best example of Egyptian mathematics. It is named after Alexander Henry Rhind, a Scottish antiquary. He purchased the papyrus in 1858 in Luxor, Egypt. It was apparently found during illegal excavations in or near the Renaissance. It dates around 1650 BC. The British Museum, where the majority of the papyrus is now kept, acquired it in 1865 along with the Egyptian mathematical leather roll, also owned by Henry Rhind. There are very few small fragments held by the Brooklyn Museum in New York. An 18 centimeter central selection is still missing. It is one of the two well-known mathematical papyri along with the Moscow mathematical papyrus. It is said, though, that the Rhind papyrus is longer than the Moscow mathematical papyrus, while the latter is older than the Rhind. The Rhind mathematical papyrus dates to the second intermediate period of Egypt. It was copied by the scribe Ahmes from a now lost text from the reign of King Amenhotep III, written in hieroglyphic script. This Egyptian manuscript is 33 centimeters tall and consists of multiple parts in which take over 5 meters long. The papyrus began to be translated and mathematically translated in the 19th century. In 2008, the mathematical translation aspect remains incomplete in several respects. The document is dated to the year 33 of the Hyksos king Apis and also contained a separate letter, year 11, on its verso likely from his successor Khumundi. In the opening paragraph of the papyrus, Ahmes presents the papyrus as giving accurate reckoning of inquiring into things and the knowledge of all things mysterious and all secrets. He continues with, the first part of the Rhind papyrus consists of reference tables and a collection of 20 arithmetic and 20 algebraic problems. The problems start out with simple fraction expressions, followed by the completion problems and more involved linear equations. The first part of papyrus is taken up by the 2 divided by n table. The fractions 2 divided by n for odd n ranging from 3 to 101 are expressed as sums of unit of fractions. For example, 2 divided by 15 equals 1/10 plus 1/30. The decomposition of 2 divided by n into unit fractions is never more than 4 terms long. As example, 1 divided by 101 equals 1/100, 1 divided by 101 plus 1 divided by 102 I meant to say 1 divided by 202 plus 1 divided by 303 plus 1 divided by 606. This table is followed by a list of fractions expressions for the numbers 1 through 9 divided by 10. For instance, the division of 7 by 10 is recorded as 7 divided by 10 yields 2/3 plus 1/30. After these two tables, the scribe recorded 84 problems altogether, and problems 1 through 40, which belong to Book 1, are algebraic in nature. Now, the Moscow mathematical papyrus is an ancient Egyptian mathematical papyrus also. It can also be known as the Golan-Chef's mathematical papyrus after its first owner outside of Egypt, which is the Egyptologist Vladimir Golchevsky. Golchevsky brought the papyrus in 1892 or 1893 in Thebes. It later entered the collection of Pushkin State Museum of Fine Arts in Moscow, where it remains today. Based on paleography and orthography of the hieroglyph text, the text was most likely written down in the 13th dynasty based on older material probably dating back to the 12th dynasty of Egypt, roughly 1850 BC. Approximately 5.5 meters long, or 18 feet, and varying between 3.8 and 7.8 centimeters, which is 1.5 and 3 inches wide. Its format was divided into 25 problems with the solutions by Soviet Orientalist Vasily Vasilyevich Struve in 1930. It is well-known mathematical papyrus, along with the Rhind mathematical papyrus stated earlier. Now, the mathematical papyrus is older than the Rhind papyrus, but the Rhind is longer than the Moscow. The 10th problem of the Moscow mathematical papyrus asks for the calculation of the surface area of a hemisphere, possibly, or the possible area of a semi-cylinder. The text of the problem 10 runs like this. Example of calculating a basket. You are given a basket with a mouth of 4.5. What is its surface? Take 1/9 of 9 since the basket is half of an eggshell. You get 1. Calculate the remainder, which is 8. You calculate 1 divided by 9 of 8. You get 2/3 plus 1/6 plus 1/18. Find the remainder of this 8 after subtracting 2/3 plus 1/6 plus 1/18. You get 7 plus 19, not 19, I'm sorry, 1 divided by 9. Multiply 7 plus 1/9 by 4 plus 1/2. You get 32. Behold, this is its area. You have found it correctly. The solution amounts to computing the area as area is equal to 2 times 8 divided by 9 raised to the second power times the diameter squared plus is equal to 2 times 256 divided by 81 times the radius squared. This means the scribe of Moscow papyrus used 256 divided by 81, approximately 3.16049, which it was to approximate pi. In ancient Egypt, it had a rich religious tradition which permeated every aspect of its society. As in most early cultures, the patterns and behaviors of the sky led to the creation of a number of myths to explain the astronomical phenomena. For example, the Egyptians the practice of astronomy went beyond legend. Huge temples and pyramids were built to have certain astronomical orientation, although many of the religious aspects of Egyptian life were known for centuries. It was not until recently that a number of archaeoastronomers attempted to find out how important astronomy really was in ancient Egypt. Foremost, the archaeoastronomers and one of the pioneers of the field, Sir Norman Lockyer, a British astronomer who lived from 1836 through 1920 and extensively studied Egyptian astronomy in his book Dawn of the Astronomy. Lockyer breaks ancient astronomy into three distinct phases. First, a civilization goes through a worship stage, where astronomical phenomena are viewed as the actions, moods, and warnings of gods. Next, a civilization progressed into astronomy for terrestrial purposes, such as for agriculture and navigation. The final step is to study astronomy solely for the sake of gaining knowledge. The ancient Egyptians started in the worship stage and eventually began to seek how astronomy could help them in their everyday lives. The Egyptian gods and goddesses were numerous and are pictured in many paintings and murals. Certain gods were seen in collections, and others were represented by actual astronomical bodies. The collection of Orion, for instance, is represented by Osiris, who was the god of death, rebirth, and afterlife. The Milky Way was represented by the sky goddess Nut as giving birth to the sun god Ra. The stars in Egyptian mythology were represented by the goddess of writing Sheshat, and the moon was either Tarath, the god of wisdom and writing, or Kronos, a child of the moon god. Many Egyptian buildings were built with an astronomical orientation. The temples and pyramids were constructed in relation to the stars and zodiacs and constellation. In different cities, the buildings had different orientations based off the specific religion of that place. For instance, some temples were constructed to align with the stars that either rose or set at harvest or sowing time. Others were oriented towards the solstice or equinoxes. So, an alternative building method that was to gradually narrow successive doors into specific rooms in order to concentrate sunbeams into the God's image that designed the God's image design. At the Temple of Metit Habu, there are actually two buildings which are slightly off kilter. It has been suggested that the second one was built when the altitude of the temple's orientation stars changed over time. So thus, with all of this, the Egyptians ended up creating a calendar and a way to invent a prototype of a watch. So all in all, Egypt's majesty stems from many different regions. One being its very beautiful art paintings of the hieroglyphs, all the way to its mathematical ingeniouses such as the fraction system. Thank you for your time, and I hope you have a good day.